Welcome back to ECE 220. We're reaching a steady state. Now we'll get into quite a few 5-day semesters, and that will lead us up to exam number 1, which is on a Thursday, the 26th of September. Prior to that, you have homework assignments 2, 3, and 4 that will be due on Tuesdays. The next one is homework number 2, and the labs begin this week. Depending on what section you are in, you will be attending lab on Tuesday, Wednesday, Thursday, or Friday, unless you are section I, and that will then be your orientation next Tuesday. But those labs are in ECE 311, and this week it's the orientation. Wear covered toed shoes and bring something to take notes with so that you can be ready to go and become oriented in that lab. The P-Spice homework, hopefully you've looked at or watched the tutorial video. That will, I hope, help you work through the first half, and the second half is somewhat of a copy. It's just now you're looking at the current divider instead of a voltage divider circuit. That homework, the P-Spice homework, is due on Friday, and that will be due in class. Means you'll have to be here on Friday unless, well, no unless. Maybe you've now become used to watching these at your leisure, but on Friday we're going to coax you back into class with your homework assignment from P-Spice. Relative to exam number 1, even though homework 4 is due prior to that, exam 1 will cover material or topics on homeworks 1, 2, and 3. And if you want some practice exams, there's a link on the website to access those practice exams. Today I want to bring us back from the weekend with a class query, combining resistors. Then we will look at this equivalence of delta and Y connections. How can we take a delta connected set of resistors and rewrite that as a Y connected set? Then we'll look at the special case where the delta or Y have equal resistors in all the locations, and then that gives us a very easy way to transform from delta and Y. And we'll look at a couple of bridge circuits. One that's unbalanced, and we'll talk about what that means for a bridge circuit to be balanced, and look at the second one where it is balanced. And in fact, a Wheatstone bridge is where you are adjusting one of these resistors to try to balance the network so that you have zero current flowing across the bridge or through the bridge. And you may hear about a Wheatstone bridge, and that's its intent. So now here's the class query. I'm not sure if those ribbons of highlight make sense. They're coming in a little different than what I thought they would, but that's okay. The labeling of this delta connection of resistors, ABC, the highlight is trying to help you orient or determine which R sub A, which R sub B goes where. If you look at the vertex for A and look directly across from it, right below it, that's where R sub A is going to be located, R sub lower A. Our delta connection will have alphabetical subscripts, R sub A, R sub B, and R sub C. And they are located opposite their vertex. What I want you now to do is answer, and here's the way that I'm going to query the class. You're going to answer with a 1, 2, 3, 4, or 5 with your hand, and you're going to place it near your chin, let's say, so that I can see what you're answering, but close enough to your chin that everybody in class won't see what you're answering. Okay? And I'll count to 3, and at the count of 3, I want you to tell me which of these combinations of R sub A through R sub C make up the resistance R sub AB. And the resistance R sub AB is the resistance. If we put a digital multimeter set to measure resistance, an ohm meter, if we connected that across terminals A or nodes A and B, what would it measure? What resistance would it measure? It will measure something associated with R sub A, R sub B, and R sub C. So, at the count of 3, show me your digits. And the digits determine your answer. And I guess an I don't know is like this. None of the above, maybe. Ready? 1, 2, 3. I'm glad we're getting some people are just wondering what to answer, right? But the answer is 4. Whatever happened there, I have no idea. So let me try. Are you kidding me? It's because I cut and pasted, I guess. So let me not be too aggressive with how I indicate the answer. The answer is R sub AB is really the parallel combination of R sub C and the series combination of A and B. And that's what 4 indicates. If we now looked at the resistance between nodes A and B, that's really the parallel combination of R sub C with R sub A plus R sub B. Question 2. What is R sub AB? And now in the Y configuration, we are using numerical subscripts. And that's to try to keep us consistent. If we want to go from delta to Y or Y to delta, we know what we are starting with and what we need to end up with. And you may have to keep me honest, but here, hopefully it's clear how the 1, 2, 3 subscripts on the R's are related to the nodes A, B, and C. 1 goes with A, 2 goes with B, and 3 goes with C in terms of how those subscripted resistors are connected most directly to those nodes. And now I'm asking, what's the resistance that you measure between node A and node B for R sub AB in the Y configuration? We ready to obtain your response? With a digit by your chin at the count of 3. 1, 2, 3. I like the creative way people are showing me different ways of indicating 3, but 3 is the correct answer for this. Because R sub 3 is really infinite in terms of if you're just holding on to node, if you're measuring from node A and node B, C is presenting an infinite resistance to that combination, and you're really just measuring the sum of R sub 1 and R sub 2. Knowing how to obtain those particular resistances between various nodes is how you determine how to convert between delta and Y connections. Meaning, now that you know or have seen what these formulas consist of between the various nodes, what's R sub AB? Now you're going to help me label the subscripts and the numerators of these expressions. Down below is the sum of those three, because in this configuration we know that it's the parallel combination of one of those with the sum of the other two. And the sum of all three is what you would put in the denominator in a parallel combination. Parallel combination of two resistors would be R1 times R2 over R1 plus R2. It's just in this case, R2 is a sum of two series resistors. What is, or what labels do I put on R sub AB? Well, I guess first I need to label the ABC. Suppose you now are saying, I need to remember this. Well, the first thing you need to do is label your ABC diagram. What goes on the leftmost resistor between nodes A and B? What's the subscript? It's across from vertex C. This is R sub C. What's the subscript on the horizontal resistor? R sub A. And what's the subscript? There's only one left. This was the hard question. This subscript, it's across from vertex B, is R sub B. Do you have now an idea as to how those are now related? The vertices and the labels on those resistors. Once we have that consistent labeling of our delta connection, now we can write down these formulas for the three different measurements that we could make on that delta configuration. R sub AB, what does that consist of in the numerator? We're measuring between nodes A and B with an ohmmeter. R sub C is now in parallel with the series combination of A and B. We okay with that? What about R sub BC? What's the first resistor subscript? A? Yeah, it's A. R sub A. And that is in parallel with the series combination of B and C. And do you see how this pattern is sort of, if you wanted to find a pattern, now you sort of have it. What is R sub CA's resistance? Well, the resistor directly between C and A is R sub B, and that's in parallel with the series combination of R sub C and R sub A. That's how you would now write down these resistance values measured across paired nodes. What if that's the delta configuration? Now here's the Y configuration. And how are the subscripts labeled on the R's, or on the resistors in this configuration, if I now have A, B, and C as labeled? What's the most vertical resistor connected to node A subscript. Now it's numerical, so it's now R1. Ooh, that's a, thought my S's were bad. 1, 2, and 3. And now R sub AB, since R sub 3 is infinite, this is now R sub 1 plus R sub 2. R sub BC is R sub 2, R sub 3, and R sub CA is R sub 3 plus R sub 1. We want to convert, or be able to, given a delta, we want to be able to convert that to a set of y's. Or, given a y connection, convert that to a delta connection. The way that we will do that is we have 3 different formulas. We have 2 for R sub AB, 2 for R sub BC, and 2 for R sub CA. We're going to set those equal and solve them for either the A, B, C's or the 1, 2, 3's. Question? Pardon? So if this is in a circuit, you have to figure out the question. I'm not quite sure I'm catching it. Right now, all we're concerned with is if we have a network that involves a delta, can we now convert that to a triangle? Or, I'm sorry, to a Y. In our bridge circuit, we had a triangle up top, or we had a delta down below. And we could convert either the top or the bottom. And once you convert it, then you can start using your parallel series combinations to get what you need. So, to make that connection for delta and y, what we're doing is we're setting these 6 equations equal in an appropriate way. We're setting the R sub AB equations together, R sub BC equations together, and R sub CA equations together, and these equation numbers are what you would find in the textbook. These are equations 12, 13, and 14 in the textbook, so you can copy those down later if you want. But do you get the idea? I've now set the deltas equal to the y's, and depending on what I want to do, I can now solve for R sub A, R sub B, R sub C in terms of R1, R2, R3, or the other way around. I have 3 equations, really in 3 unknowns, assuming I know the other 3 variables. You've seen the cartoon, right, where somebody's at the board and there's all these equations and then they say magic happens. Well, it's not magic, it's algebra. And I'll try to post a link to what I've provided the algebra before to 320 students when they take this, when they have not R's but Z's, where Z's are complex. But I still talk about Z sub A, Z sub B, and Z sub C. They're in the exact same location, and correspondingly Z1, Z2, Z3. You just think R's instead of Z's when watching. But if you now do the algebra, here is what you will end up. You can now find Y's in terms of deltas. We're going now from alphabetical subscripts to numerical subscripts. Now we're assuming that we have our connection in a delta, and we want to find what it looks like in Y. And we talked about how we would find that. If you look at, in a sense, if you looked at I can't draw today, but you get the idea. Here's the delta, and then you can think of connecting that. These are not, all connected simultaneously. You're replacing the solids with the dots or the dashed. But if this is now A, and this is B, and this is C, then this was R1, and this was R what? On the leg of the triangle from A to B. What was that? It's opposite vertex C. This is R sub C. And this was opposite R vertex B. That's R sub B. And R sub 1 is in the vertical, meaning to go from delta to Y, you look at R, you want R1's value. You say, oh, R1 is actually touching R sub B and R sub C. That's the product I'm going to end up with in the numerator. And downstairs, it's just going to be the sum, RA plus RB plus RC. That's how to go from delta to Y to obtain R sub 1. R sub 2 is likewise, where's R sub 3 in this diagram? Bottom right. So here is R sub 3, and this is R, there's only one left. This is R sub A. So how do I now write R sub 3? What's its formula? R sub 3 touches R sub A and R sub B, and it's over RA plus RB plus R sub C. That's how you could find these different Y resistor values in terms of delta resistor values. By looking at what the Y resistor is touching, or what's on either side of it, and then writing down that power or that product in the numerator. And then in the denominator, it's just the sum. That's how to go from delta to Y. To get Y to delta involves more algebra, but now this is how it's done. You really just have in the numerator the pairwise combinations, the sum of pairwise combinations of the Y resistors. R1 times R2 plus R2 times R3 plus R3 times R1. Boom, you write that down. The pairwise, the sum of the pairwise combinations of the Y resistors. Then, to obtain the denominator, we look at this triangle again, and we say, oh, I want R sub A. Well, what's sort of between R sub A and the A is R1, or what's furthest away from it is R1. That's what we're dividing by in this formula. So what do we divide by to obtain R sub B in the denominator? R sub 2, because that is now right here. And process of elimination, R sub C. Oh, if I look towards the C vertex, I'm going to run into R sub 3, or R sub 3 is furthest away, however you want to remember it. There's now the way to relate or go from Y connections to deltas. The numerator is always the same in 18, 19, and 20. So now let's use that if somebody gives us equal resistors. And let's just start with the delta and find what these resistors need to be in the Y's. If all of our R sub A, R sub B, and R sub C, and we really don't need to label these, but you could say, oh, I'm having This is now R sub C, this is R sub B, and this is R sub A. But they're all the same, so it really doesn't matter. But if we now want to find R sub 1, what was that going to be? We want to go from delta to y. We go back up here, and here's our delta to y formula. It's the product of the two resistors that R sub 1 touches divided by the sum of those, all three of those resistors. So if this is now R sub 1, its formula, I've written it down already for us. What's R sub B? In this assumed equal resistor case, we're calling it 3R. R sub B is 3R. What's R sub C? 3R. What's R sub A? Well, that's 3R. R sub B is 3R. R sub C is 3R. So what does that give us? That now gives us 9R squared over 9R. The 9's cancel, one of the R's cancel, and we see that if we started with equal resistors of value 3R in the delta, the Y's are just a third of that. They are just R. Or if we sketched that, doesn't really matter, but if you're redrawing this in some network, you may need to keep track of the nodes A, B, and C. But if this is now 3R, 3R, and 3R, and you wanted to replace that with a Y, what would that ugly vertical resistor be? You would just replace, you would erase those delta resistors and replace them with this Y set of connected resistors and change the numerical value on those resistors to 1/3 of what they were in the delta. Or vice versa, if you now see a Y connection in a network of resistors and you say, I could simplify this better if they were now in a delta connection, you would then triple their numerical value and replace the Y set with R's. And now you might be saying, well, I'm not going to remember all of that. Well, remember the picture. What is inside the other? The Y is inside the delta. The Y is inside, so it has to be a little smaller. So it's R, and the other is 3 times that. That's maybe your intuitive way or memory way to say that, oh, my Y is inside the delta. The Y's R's are smaller. Y? No. W-Y-E, not W-H-Y. We good on transforms, transforming Y's and deltas. Now we can put that to an application. Let's apply the Delta-Wye conversions into a bridge circuit. And in this bridge circuit, maybe what you're being asked to find is the voltage dropped across that rightmost 12K resistor. And you're going, I don't see that looking like a bridge at all. But if you start morphing those wires, extending some and shortening others, you can make the left circuit be equivalent to the right circuit. And I want you now to label. I've already given you a little bit of a hint. You know what one of those resistors will equal, I hope, just based on the way I've labeled it. What's the resistor associated with V sub 0? That better be 12K, since that's what it was in the original drawing, right? We want that resistor voltage. That's what we're trying to find, V sub 0, and that we've now collapsed the wire in above the 12K. And where did this resistor go? It now went over here. It's now turning on its side. This is now 12K. Where did this resistor go? It really didn't move, did it? It stayed put, in a sense. And now you just have to sort of see what's left. That went there, and what's left is the 16K. We okay with redrawing the circuit. Now it looks more like a bridge. And the very first step we want, if we now see a bridge network of resistors, the very first thing you probably want to do, because it will simplify your analysis, is to ask, is that bridge balanced? And what does it mean to be balanced? To be balanced, you need this particular current going through the bridge to be 0. Or if there's 0 current going through a resistor, what do you measure the voltage? Or what voltage do you measure? 0. So the voltage is 0 and the current is 0 across that bridge if it's balanced. And we will show in a little bit that really what that amounts to, or a way to check if a circuit is balanced or a bridge network is balanced, is to, I'm running out of colors, but bear with me. This is going to be very bright. But now we're essentially looking diagonally across the bridge, and we form their product of resistors. This is the quick check. You'll form that product, so we have 8K times 12K, and then we compare that with the other diagonal, which is 12K times 16K. Is that product, or those two products, equal? No. So what we've done is, in this case, this is now R1, this is R sub 3, this is R sub 4, and this is R sub 2. The odds are on the left and the evens are on the right, and this is R sub 5 in our bridge network diagram. R1, R3, R2, R4, and on the bridge is R sub 5, just to keep our notation consistent. What we're saying is, if our bridge is balanced, R1 times R4 needs to equal R2 times R3. So that's what I'm saying, resistors diagonally across R5. Is that true in this case? Is the bridge balanced? Is 8K times 12K equal to 16K times 12K. So 8 is not equal to 16. It's not balanced. And the title of this example told you that answer to begin with. This was an unbalanced bridge network. If the bridge had been balanced, here's just some text, then the current across through that bridge would have been 0, I-5 would have been 0, and then we could have applied current division immediately. Now, I hope that you guys did buy your virtual reality glasses for this class. That was one of the purchases you were supposed to make in the bookstore. You can get them out now. So put on your virtual reality glasses, and what I want you to see is I-5 is equal to 0. If I-5 is equal to 0, what do you now need to do with your virtual reality glasses? Just erase that resistor. You can erase that resistor virtually because there's no current through it, there's no voltage across it. That means that this node that I'm calling the odd node and the even node, O and E, what's the voltage dropped across those? If there's no current, if this was a balanced circuit and that resistor was removed, if you remove that, do you see that you could now just have two parallel branches and you could use your current divider to find the current through the middle branch or the rightmost branch if it was balanced. That's why in the first step when you see this network you say, is it balanced? I sure hope so because it'll make my analysis easier. If it's not, then you're forced to do what we're doing now, which is looking at this. I know it's a mess, but looking at this, you now should see deltas and Ys in that bridge network. Are there deltas or Ys such that the resistors in the delta or in the Ys are all equal? Do you see that in this bridge network? Do you see a delta that has all of its R's equal, or do you see a Y that has all of its R's equal? I'm hoping this, I know you're not seeing this on the video, but I was staring down, trying to get you to look at the bottom of the bridge network. The bottom triangle, the bottom delta, has a 12K, a 12K, and a 12K. Equal. Equal means it's going to be easier to convert from delta to Y. It's just a division by 3 to go from delta to Y. If that's the case, so here it's not balanced, convert either the top delta or bottom delta of bridge network. Is top or bottom easier to convert? Top is easy. Wow, I made such a big deal about looking down, I can't even remember. The bottom is easier. And if that's the case, I've copied down my 8 and my 16. What are the values in the Y that I've now replaced? They were 12, were they not? In the delta, what are they in the Y? Bigger or smaller? Where's the Y relative to a delta if you had to combine or put them into stacking arrangements? The Y was inside the delta, wasn't it? The Y is smaller by a factor of, how many resistors are there? 3. So 3, 12 divided by 3, and they're all the same. This is now 4K, 4K, and 4K. And let me say this is now I1, this is I2, and can you find I sub 2 for me, or a formula for I sub 2? How are I1 and I2 related to the source that's pushing 20 milliamps through both of those? Do you see that you can now apply a current divider between the two branches? You can really neglect the bottom 4K when you're doing this current divider because it's in common with both branches. But now what do we need to do for the current divider? Well, I'll do the hard part. It's going to have to be multiplied by the original 20 milliamps. What's the formula look like in a current divider? And now you're used to seeing R1 and R2. And we're talking now R2. We want to know what's the current through R2. Well, R2 in this case is 16K and 4K. What's R1? 8K and 4K. The current divider was something upstairs divided by the sum of everything downstairs, was it not? The sum of everything downstairs is 8K plus 4K plus 16K plus 4K. And what's upstairs? If I want I sub 2, it's the opposite branch, isn't it? So this is now 8K plus 4K. And if you do that math, you'll find that I sub 2 is 7.5 milliamps. What were we wanting to end up with? Are we completely... What I should have maybe done is labeled these nodes to begin with. Suppose I label this one as A, this one as B, and this one as C. Can we now label those over here? Is this A, B, and C? And we wanted to know the voltage from B to C. V naught. That now becomes that voltage, V naught. How do we find that voltage? Do you see I2 is going to, Ohm's law is what we're using. V naught is 4K times what current? I'm now talking about the voltage dropped across that resistor. What current is flowing through that resistor? I2. Plus this 4K, maybe I should have done this. What current is flowing through that 4K resistor? If you look at this carefully, do you see that I1 and I2 were dividing 20? Well, you're putting I1 and I2 back together again. 20 milliamps is now flowing through that bottom 4K. And I didn't label it as anything, so let me just call it this. And I sub 2 what's 4 times 7.5? 30. and the K and the milli cancel. 420s are 80. Do you see that V naught is 110 volts? That was what we were trying to find. We did some analysis. We had to do quite a bit of analysis. We had to, morph the circuit, turn it into something that looked bridgey. Then we looked at that and we said, oh, there's 3 resistors in a delta that are equal. Let me convert that to a Y. Oh, now I can do a current divider. And now I can do Ohm's law to find V sub 0. So if you wanted to find the equivalent resistor of this mess, is that what you're asking? Now you could do that. You could sum 8 and 4, they're in series. You could sum 16 and 4, they're in series. Now take the parallel combination of those two, the 12 and the 20, and then add that parallel combination to 4, and that's your equivalent resistance of that entire network. I think that was the question. Wow, I must have had more ideas floating around. I did, but I'm going to skip over those. What you can do is you can now find the voltage drop from A to C and compare that to the voltage drop V sub 0, and they're going to be different because this bridge was not balanced. A and B are not, the voltage dropped across them. That was V sub 5. That's going to be non-zero. Let's look at the case where that's not the case. Let's look at a balanced bridge. If we have a balanced bridge, what are the conditions? The conditions for a bridge to be balanced is we want that R5 resistor to essentially not be important. We want zero current through that bridge resistor. We want I sub 5 to be 0, and or we want V sub 5 to be 0. If that voltage drop is 0, what if I did a KVL around the top? What if I did a KVL T? Would it be R1 I1 plus V5 minus R2 I2 equaling 0? And if our bridge is balanced, that's 0, and we're left with R1 I1 equaling R2 I2. What about the KVL at the bottom? Which way do I want to do that? Let me just go ahead and do it this way, which is the opposite, which is what I shouldn't have done, but I did. The bottom KVL is now V sub 5 plus R4 I4 minus Ohm's law R3 I3, which is 0. And if it's balanced, that's 0, and we're now left with R3 I3 equaling R4 I4. We have these two relationships. But if we're balanced and I5 is equal to 0, how are I1 and I3 related? If I5 is 0, can you see if we did a KCL at the odd node, we would have I1 in, I3 out, and I5 out, but I5 is 0, so I1 and I3 are the same. Do the right side. I2 and I4 are the same. Now let's just take the ratio of R1 I1 with R3 I3, R2 I2 over R4 I4. And what I tried to argue by KCL with I sub 5 equal to 0 is I1 is the same as I3, and I2 is the same as I sub 4, and there's our balanced condition. If we cross multiply, do you see we end up with R1, R4 equaling R2, R3? That's what we were wanting to do. We're completely out of time. We have to stop the bridge discussion, and we'll pick up somewhere close to that tomorrow.